right, let's take a look at Chapter 18, Inference in Practice. In Chapter 18, we cover conditions for inference in practice, cautions about confidence intervals, cautions about significance tests, planning studies, sample size for confidence intervals, and planning studies, the power of a statistical test. Z procedures. So far, we have met two procedures for statistical inference. When the simple conditions are true, the data are an SRS, the population has a normal distribution, and we know the standard deviation sigma of the population, a confidence interval for the mean mu is x bar plus or minus z star times sigma divided by root n. To test a hypothesis, H naught of mu is equal to mu naught, we use the one sample z statistic of z equals x bar minus mu naught divided by sigma, which itself is divided by root n. These are called Z procedures because they both involve a one sample Z statistic and use the standard normal distribution. Conditions for inference in practice. Any confidence interval or significance test can be trusted only under specific conditions. Where the data comes from matters. When you use statistical inference, you're acting as if your data are a random sample or come from a randomized comparative experiment. If your data don't come from a random sample or randomized comparative experiment, your conclusions may be challenged. Practical problems such as non-response or dropouts from an experiment can hinder inference. Different methods are needed for different designs. There is no cure for fundamental flaws like voluntary response. What is the shape of the population distribution? Many of the basic methods of inference are designed for normal populations. Fortunately, this condition is less essential than where the data comes from. Any inference procedure based on sample statistics, like the sample mean X bar, that are not resistant to outliers, can be strongly influenced by a few extreme observations. Conditions about confidence intervals. A sampling distribution shows how a statistic varies in repeated random sampling. This variation causes random sampling error because the statistic misses the true parameter by a random amount. So the margin of error in the confidence interval ignores everything except the sample-to-sample variation due to choosing the sample randomly. The margin of error doesn't cover all errors. The margin of error in a confidence interval covers only random sampling errors. Particular difficulties such as undercoverage and non-response are often more serious than random sampling errors. The margin of error does not take such difficulties into account. Cautions about significance tests. Significance tests are widely used in most areas of statistical work. Some points to keep in mind when you use or interpret significance tests are how small a p is convincing. The purpose of the test of significance is to describe the degree of evidence provided by the sample against the null hypothesis. How small a p-value is convincing evidence against the null hypothesis depends mainly on two circumstances. If H0, if the null hypothesis represents an assumption that has been believed for years, strong evidence, a small p, will be needed. If rejecting the null hypothesis means making a costly changeover, you need strong evidence. Significance depends on the alternative hypothesis. The p-value for a one-sided test is 1/2 the p-value for the two-sided test of the same null hypothesis based on the same data. The evidence against the null hypothesis is stronger when the alternative is one-sided because it is based on the data plus information about the direction of possible deviations from the null. If you lack this added information, always use a two-sided alternative hypothesis. Sample size affects statistical significance. Because large random samples have small chance variation, very small population effects can be highly significant if the sample is large. Because small random samples have a lot of chance variation, even large population effects can fail to be significant if the sample is small. Statistical significance does not tell us whether an effect is large enough to be important. That is, statistical significance is not the same as practical significance. Beware of multiple analysis. The reasoning of statistical significance works well if you decide what effect you are seeking, design a study to search for it, and use a test of significance to weigh the evidence you get. Planning studies. Sample size for confidence intervals. A wise user of statistics never plans a sample or an experiment without also planning the inference. The number of observations is a critical part of planning the study. The margin of error, ME, of the confidence interval for the population mean mu is M equals Z star times sigma, which is divided by the square root of n. To obtain a desired margin of error M, put in the value of Z star for your desired confidence level and solve for the sample size n. Sample size for desired margin of error. The Z confidence interval for the mean of a normal population will have a specified margin of error M when the sample size is n equals to the quantity Z star times sigma divided by M squared. Planning a study, the power of a statistical test. How large a sample should we take when we plan to carry out a test of significance. Here are the questions we must answer to decide how many observations we need. Significance level. How much protection do we want against getting a significant result from our sample when there really is no effect in the population? Effect size. How large an effect in the population is important in practice? Power. How confident do we want to be that our study will detect an effect of the size we think is important? The power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level alpha when the specified alternative value of the parameter is true. Example, a matched pairs experiment to test for loss of sweetness. The bigger the difference, the bigger the loss of sweetness. We know the sweetness loss scores vary from scorer to scorer according to a normal distribution with standard deviation about sigma equals 1. To see if there is a loss of sweetness, we test. The null hypothesis is that mu equals 0. There is no difference. There is no loss of sweetness. The alternative hypothesis is that mu is greater than 0. Therefore, there is a loss of sweetness. Will 10 tasters be sufficient for this study? Or should we use more? Significance level. Requiring significance at the 5% level is enough protection against declaring there's a loss in sweetness when in fact there is no change, if we could look at the entire population. Effect size. A mean sweetness loss of 0.08 of 0.8 of a point on the 10-point scale will be noticed by consumers, and so is important in practice. Power. We want to be 90% confident that our test will detect a mean loss of 0.8 point in the population of all tasters. Result from Minitab. We see that our earlier sample of 10 tasters is not large enough to be 90% confident of detecting at the 5% level an effect of size 0.8. If we want power 90% against effect size 0.8, we need at least 14 tasters. The actual power with 14 tasters is 91%. So if you look at the little chart to the side, we have difference in tenths listed in a column. We have sample sizes listed in a column. We have the target power, which is 90%, 0.9, and then the actual power. So they calculate for us what sample size would get us closest to our target. And for a 0.8 to get us closest to a 90% target, we need 14 people. How large a sample should we take when we plan to carry out a significance test? The answer depends on what alternative values of the parameter are important to detect. Here is an overview of influences on how many observations do I need. If you insist on a smaller significance level, such as 1% rather than 5%, you have to take a larger sample size. A smaller significance level requires stronger evidence to reject the null hypothesis. If you insist on higher power, such as 99% rather than 90%, you will need a larger sample. Higher power gives a better chance of detecting a difference when it is really there. Any significance level and desired power, at any significance level and desired power, a two-sided alternative requires a larger sample than a one-sided alternative. At any significance level and desired power, detecting a small effect requires a larger sample than detecting a larger effect.